Hey everyone, welcome back to my channel. In today's video, we are tackling one of the most classic problems in computer science, the coin change problem. Here is the setup. You are given a set of coin denominations, for example 1 cent, 5 cents, and 6 cents, and a target amount you need to make. Our goal is to find the minimum number of coins needed to reach that exact amount. For example, let's say the target is 10. The question is, what is the minimum number of coins that we need to use in order to reach that 10 cent? So, formally we can say, given a set of coin denominations and a target sum, find the minimum number of coins that add up exactly to that sum. It sounds simple, right? And in many cases, a greedy approach, which is always picking the largest coin first, works perfectly fine. But today, we will see exactly why greedy fails in some situations, and why dynamic programming is the correct, guaranteed solution. Let's first see where can we use this algorithm. The coin change problem isn't just a textbook exercise. We can find it in ATMs and vending machines, where they need to dispense change using the fewest bills or coins possible. Or we can see it in point of sale systems, in which they are calculating optimal change for a cashier. We can also see it in game development, in currency systems, where players collect minimal items to reach a goal. And most importantly, we can see it in resource allocation, which is minimizing the number of operations to reach a target state. Actually, today we will see that the coin change problem is a gateway to understanding the power of dynamic programming. Once we understand why greedy fails here, we start seeing dynamic programming opportunities everywhere. Let's try to see why greedy solution does not work for this problem. Let's say we have the following coin denominations, 1, 5, and 6, and the target amount we want to reach is 10. Our goal is to find the minimum number of coins needed to make exactly 10. Greedy solution starts with sorting the coins in descending order. Then it states that we need to pick the largest coin that fits the remaining amount. And we will repeat it until the remaining amount is 0. Let's create a table and track what we are doing in each step. In the first step, the remaining amount is 10, since we haven't chosen anything yet. We are looking the reversely ordered list and took the largest coin, which is 6, right? Because we have denominations of 1, 5, and 6, so the largest is 6. Since it's less than the remaining amount 10, so we can use it. We put it into our bucket, so the number of coins used so far is 1. In the next step, we are again looking at the list, but we can't use 6 and 5 anymore, since the remaining amount is smaller. So we need to use coin 1. We continue to do the same thing until the remaining is 0. As we can see at the end, we have used 5 coins by using the greedy approach. But is it the optimal solution though? Unfortunately, it's not the optimal solution. The optimal solution is 2. Greedy directly chose the largest one and disabled the possibility of using 5 two times. We can solve it correctly with dynamic programming, since it uses previously solved subproblems to reach the optimal result. We have our recurrence relation, stating that either take it and decrease the remaining, or not take it, based on whichever gives the minimum result. As you remember, in dynamic programming, we are starting with initializing our dynamic programming table, which we call DP table. Columns are the possible target values up to the real target. Since our target in this case is 10, we wrote every possible target values between 0 and 10. And rows are representing the coin denominations. As you remember, we have 1, 5, and 6. Since we want to minimize something, we need to put the highest value for the valid target values. When target is 0, we can't use any coins, so the number of coins is 0. But for the others, we are initializing them as infinity, so that whenever there is a smaller value, we can take that. After we completed the initialization step, we are starting the recurrence. And let's walk through it together for our example. Starting with the first row and the first column, I'm trying to see if I take this queen, is it going to decrease the minimum? So we are assuming that our target is 1 and we will either use this queen or not. Looking the upper row, which represents the scenario where we are not taking this queen, it's infinity. So I'm also looking what will happen if I use this queen and taking the minimum one. In this case, taking this queen is the minimum. So I am taking it. When the target is 2, we need to use this queen 2 times, which is again less than infinity. And when the target is 3, it will be 3 times, and when it is 4, it will be 4 times, and so on. When the coin value is 5, as you can see, until the target is 5, we can't use this coin because it's more than the target value. When the target value is 5, again we need to look which option is the best. If I don't use that coin, then I need to use 5 coins. As you can see on the upper row, there is 5. So it means that if we don't use this coin 5, we need to use 5 different coins in order to satisfy this target value. But if I use this coin, then we only need to use 1 coin. So since it is smaller, I'm taking this coin. When the target is 6, if we take this coin, then we need another coin to adapt this target. So we need to use 2 coin. We are continuing to do the same thing and take the minimum. When the target is 10, if we take this coin, we will have 5 cents remained. And we can go here and see that we can satisfy that by using just 1 coin too. So that means we can add up to 10 by using 2 coins. For the 6-cent coin, again, we can't use this coin until the target is at least 6. We are doing the same steps and taking always the minimum. For example, when the target is 6, I'm looking at is it better to take that coin or not. If I don't take that coin, I need to use 2 different coins, as you can see on the upper row. But if I use that coin, then I need to only use 1 coin. So, since 1 is smaller than 2, I'm taking that coin into my pocket. And we are doing the same steps and taking always the minimum. Be careful when the target is 10 again. If we use 6-cent coins, then we will have 4 cents remained, and we can only satisfy it by using 4 coins. But we have a smaller value if we don't use 6-cent coin, so we are not using it. And at the end, we are getting the final result of 2 at the last cell. Let's see our judge board of the week. For the coin change problem, we have seen 2 different approaches. As we saw, greedy is fast, but not always correct. As we saw in our example, for arbitrary coin denominations, it can give a suboptimal answer. In that case, we saw 5 coins, right? Although the optimal result is 2. On the other hand, dynamic programming builds the solution bottom-up, using previously solved subproblems to guarantee the optimal results all the time. So, for the coin change problems, we need to use dynamic programming all the time. In the next video, we will look at the activity selection problem, a case where the greedy approach is probably optimal. It will be a great contrast to today's problem and show you how to recognize when greedy is safe to use. If you found this helpful, please like and subscribe. See you in the next one.